Hi there. This lesson is about unit vectors, and what you need to know about unit vectors is that they give you a way of expressing a vector in more than one dimension. So if you have a vector that you want to express in 2 dimensions or 3 dimensions, unit vectors are a great way to do that. Unit vectors allow you to break down a vector into its components and express it mathematically by its components. Okay, so I'm going to start off with a statement that unit vectors are directional placekeepers. And here's what that means. If you think about having a coordinate system where you have kind of your x direction and your y direction, well, a unit vector is going to be a vector that lies along one of those axes that has a length equal to 1. And so that's why it's called a unit vector, because unit means 1 in math. So the unit vector that points in the positive x direction is called an I hat vector. I put a little caret or a hat on top of that. And the letter I indicates that we're going to be going in the positive x direction. Okay? Seems kind of strange, but that's what it is. In the y direction, you have the same thing. You can imagine a vector that's 1 unit long. And this vector is called a j hat vector, or just a j vector. And so these are directional placekeepers. So the I hat vector always points to the right. The j hat vector always points up. And really, their magnitudes don't matter much. And so we make the magnitudes 1 so that we can use those vectors to represent other vectors in terms of them. Okay, I will show some examples here. So again, the magnitude of the I hat vector, right, if I put these absolute value bars on it, it's going to be equal to 1. And so is the magnitude of the j hat vector. Okay, so this is why they are called unit vectors, because unit means 1. Okay, so let's see why this is actually like a good thing, and why you care. So let's take an example. I'm going to sketch a vector here, and I'm going to say that this particular vector is going to come out by 4 in the x direction, and then I'm going to make it go up by 3 in the y direction. And we'll make it point in that direction. So this is a position vector, okay? A position vector. So it would have coordinates 4, 3. The head of that vector goes to 4, 3. And we are going to label that vector with a lowercase r. That's oftentimes used for vectors in 2 dimensions. The r is for radius. And I'm also going to indicate that that's a vector by putting a half arrow above it, a half arrow. So you have to kind of keep track of these different symbols here. That half arrow is a symbol for any vector. The hat that we showed earlier is the symbol for just a unit vector. The hat is a very special symbol. Okay. All right, so let's express this vector in unit vector notation. So we want to express r in terms of the I hat and j hat vectors. And so the way that you would do that in this case is that you would say you have 4 okay? In the I hat direction, plus 3 in the j hat direction. And that literally means that you are doing a vector addition thing, okay? So remember, my I hat vector is this guy right here, right? That's 1 I hat. So if I multiply that by 4, well, we know that multiplying any vector by a scalar, like the number 4, brings it out and lengthens it. So this would be my 4 I hat. And then what I do is I imagine adding another vector to it using the head to tail method. So if this is j hat right here, I would multiply that by 3, and that brings me up to there. And so now I've got my head to tail method where I'm adding my 4 I hat plus my 3 j hat. And the resultant is this vector. And so I've basically just written down the R vector in terms of its components. Okay, and so that's how you do this. Something that you can do with this, if you want to find the length of the R vector, I hope you all know that that's going to be 5, right? Because this is a 3, 4, 5 triangle. But like formally, if you want to find that length, of course you just do 4 squared plus 3 squared and take the square root. And of course that's a Pythagorean theorem. Okay. And so that's how you do that. So that's pretty, I mean, it's just all we've introduced here is slightly new notation. In general, in 2 dimensions, you can talk about like expressing a vector as x times I hat plus y times j hat. And x and y are just numbers. Those correspond to the distances along the axis. Okay? And of course, your magnitude is going to be the square root of x squared plus y squared. Okay? And if you wanted to find this angle, theta, of course, tangent is the way to go. Tangent is opposite over adjacent. And so to find the angle here, in this case, you would take the inverse tangent of y over x. And I think if we do that in this example, we should get something like 36 degrees, I believe, 37 degrees for a 3, 4, 5 triangle. Okay? All right, so the only other things to show then would be how you can do displacement and velocity and acceleration with unit vectors. And it's really not a lot more. Okay? So let's do one example here where we have, let's say that this is my initial position vector. Okay? So we're going to make that equal to 5, like maybe 5 meters. So this vector is 5 meters long. Of course, we probably should draw the origin here. And of course, the x-axis keeps on going. So this might tell me exactly where something is initially. Let's say that sometime later, the object ends up in a new position, okay, given by this vector, our final. And why don't we use the kind of the values that we had used before? So let's make this go to 4, 3. Okay, so this is going to this is a hypotenuse of a 3, 4, 5 triangle. Okay. Now, a big question here that I hope you realize is that if I say find the displacement of the object, find its change in position, it's delta r. I hope we all know that you'd find that by taking the r final minus r initial, because whenever you have a change in something, it's always final minus initial. Now, what would that look like in this picture? Let's at least sketch it. Okay. If I take our final, which is this guy here, and then I subtract our initial, which is this here, what would that look like? Okay. So our final minus our initial is going to be like our final plus negative our initial. And this is all somewhat confusing, but that means that you're going to actually have to imagine taking this vector and adding the negative r initial to it. Oh my gosh, right? And so it looks like that's going to bring us into this second quadrant. This is going to give us delta r. That's kind of complicated, right, to draw it that way. So there's a faster way to do it. And the faster way, if you want to find this, is to simply connect the initial to the final, okay, the heads of those vectors. And so can you see that this vector that I'm sketching here is actually the same length and the same direction as the other one? So you may have to play around with that a little bit. But the idea is that, if you want to find displacement, I guess common sense kind of tells you that if the object starts right here and it ends right here, well, its displacement is going to be the connecting vector between those 2 points. Maybe that's the best way to explain that. From a unit vector point of view, this is what this is going to look like. From a unit vector point of view, you have to subtract the x parts of those vectors, and you leave those in front of the I hat vector, and then you do the same thing for the y pieces. So you have to subtract the y values multiplied by the j vector. So let's do that. So let's see. 4, 3 are the coordinates for my final position, and it looks like 5, 0 would be the coordinates for my initial. So when I do x final minus x initial, I want to do 4 minus 5. Okay, of course that's going to give me negative 1. And that kind of makes sense because this vector that I'm getting is kind of angling backwards by 1 unit. And then we repeat it for the y direction. And so we would take y final minus y initial. That's going to be 3 minus 0. In the j hat direction. And of course that just gives us negative 1. I'm sorry, 3 in the j hat direction, okay, which means I go 3 up. So, it's pretty straightforward that all you're doing here is doing a subtraction with the x pieces and with the y pieces, and that's how you find the difference between two vectors like that. Again, if you want to find the length of that vector, you could just do, so if this is your displacement vector itself, then the length of that is going to be equal to negative 1 squared plus 3 squared, square root, and so on and so forth. So that's the power of doing this way. And clearly you can add together or subtract as many vectors as you want. But to find displacement, you're subtracting final minus initial, and that's how you do it. Okay, almost done. Let's talk velocity. And we know that velocity is equal to the derivative of a position vector with respect to time, right? And so here again, this is like a radius. So what does that look like with unit vector notation? What that's going to look like is going to be the derivative of the x piece in the I hat direction plus the derivative of the y piece in the j hat direction. And so that's how you find velocity if you know the position vector in unit vector notation. So let's do an example like this. Let's say that my position vector for this object as a function of time is going to be equal to 10t in the I hat direction plus 5t squared in the j hat direction. And so the velocity then would simply be the derivative of those two things. Okay? And so the derivative of the first term is 10. And the derivative of the second one is going to be 10t. And I'm not indicating units here because I'm just not wanting to write them down. But clearly the units here would have to be meters per second, and the units of 10t also have to be meters per second. So just be aware of that when you're doing things with these expressions. Acceleration, I won't do an example with it. I'll just kind of give you the formal statement for that. Since velocity looked like this up above, acceleration will have a very similar definition, except it's the derivative of velocity with respect to time. And so you can say something like this is going to be dvy dt, I'm sorry, dvx dt in the I hat direction, plus dvy dt in the j hat direction. And so, of course, in order to evaluate this acceleration, you have to know the velocity as a function of time. And I think you could imagine what types of functions we could put in for things like that. So it's the same story as what we did up above. You have to be given, a velocity function in its unit vector notation before you can do anything with this. But anyway, the unit vectors really let you break things down into components. That's why they're so valuable. And so we like them. They are great in 2 dimensions and in 3 dimensions, although we'll just be doing 2-dimensional problems in this class. And they allow you to just take that component method approach and apply calculus to the different directions separately to come up with really good answers. Okay, so hopefully that's helpful. And we will use that in class. See you later.